So we are getting into a next portion of our class, the last portion of our class, new material, which is sequences in series. Okay, so sequences is just a range, ordered set of numbers. Your book defines it a little differently, so I just kind of want to give you the same definition as they give it. So the definition of a sequence is a function whose domain is a set of positive integers and whose range is a subset of real numbers. So a sequence is a function whose domain is the set of positive integers and the range is a subset of the real numbers. Okay, so we've been dealing with functions before. We talked about domain and range. When we had functions, we had some, you have function notation, f of x equals, and then we had an expression on how to relate x in terms of y. This is just saying that the values that we're plugging in for x has to be a positive integer. So the values that we're going to be plugging in for x are 1, 2, 3, 4, 5, etc. So we're not going to put in a fraction of those values, or we're not putting in negative values. And so that's where we come in with the positive integers. And then any value that you plug in for, usually it's n in this case, the variable that we use for sequences, you're going to get some output. There's going to be some equation that you're going to use to figure out what your output is. And that output is usually a real number. Okay. When we're dealing with sequences, instead of function notation to determine the equation, we use little letters and a little subscript, a sub n. So a sub n, b sub n, c sub n, these are things that represent the function. And gives you the nth term of the sequence. So a sub n, this could equal, well, I don't know what it is, a sub 1, a sub 2, a sub 3, a sub 4, dot, 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 a sub n. Sometimes it's infinite, so it can go on forever. This a sub n value is basically, again, the equation that you're going to use to get your terms. This 1 here, this tells us this is our first term. And this is where we let n equal 1. So this is our second term, the next term, a sub 3 is our third term. So if you see a sub 3 equals something, that's telling us that our third term is equaling that. So there's different types of sequences. So let's look at just one example. So let's say you are given a sub n and it wants you to list a certain number of terms. So we're given that a sub n is equal to 2n plus 1, and then that's our numerator, and that's all over 2n. So list the first 5 terms of the sequence. So just like when we were looking or evaluating something at f of 1, we would go back in and we would plug in 1 wherever we saw, wherever that function, whatever variable we were looking at. In this case, we're looking at 1, n. A lot of times it was x. So if I want to look at a sub 1, all I'm doing is I'm going back into this, this is our formula, and plugging in 1 wherever I see an n. So I have 2 all times 1 plus 1 all over 2 all times 1. So just simplify it. And so simplifying it, we have 2 times 1 is 2 plus that 1. That's going to give us 3. All over 2 times 1, which is 2. So that's the first term in our sequence. The second term in our sequence we can get by going in and plugging in 2 wherever we see an n in our equation. So looking at a sub 2, we have 2 times 2 plus 1 in the numerator all over 2 times 2. And so this would give us back 2 times 2 is 4 plus 1 is 5 all over 2 times 2, which is 4. So that's our second term of our sequence. Our third term of the sequence, plugging in 3 wherever we see an n, we get that a sub 3 is equal to 2 times 3 plus 1 all over 2 times 2. I'm sorry, 2 times 3. So 2 times 3 is 6, 6 plus 1 is 7, 7 all over 6. So we're going to do this 2 more times because I wanted the first 5 terms. So if I do a sub 5, this is a sub 4, this is equal to 2 times 4 plus 1 all over 2 times 4. Well, 2 times 4 is 8. 8 plus 1 is 9. 9 all over 2 times 4, which is 8. And one more time, a sub 5. So plugging in 5 wherever you see an n, we have 2 times 5 plus 1 all over 2 times 5. So this gives us 2 times 5 is 10 plus 1 is 11 all over 2 times 5, which is 10. So our sequence, if I started to list out my first 5 terms, I have 3 halves, 5 fourths, 7 sixths, 9 eighths, 11 tenths, ... So it goes on in this sequence forever in this form. So sometimes we want to go backwards. Sometimes we're given a sequence and we want to figure out, how can I figure out the formula for that nth term? So look at this in here. Notice that our numerator is all odd numbers, 3, 5, 7, 9, 11. So the next one we could tell is going to be 13, 15, 17, ... Notice our denominators are all even numbers, 2, 4, 6, 8, 10, and it's going to go on that pattern forever. We talked about, I think in the past, that all odd numbers, actually that was probably more in my trig class, but odd numbers are in the form of 2n plus 1. So you can always write an odd number in that form, and an even number could always be written in that form of 2n. And so that's going to be helpful for us to know soon. So note, odd numbers can be written in the form two n plus 1, where n is an integer. Even numbers can be written in the form two n. Again, n is an integer. So sequences aren't too bad. It's pretty much just finding terms of a sequence. So you're just basically plugging in integers, starting usually at 1, 2, 3, 4, etc. And wherever you see an n in your formula for the nth term. And those can give you terms of the sequence. So let's look at another example. So let's say that you have S of n is equal to, so the curly brackets represent sets. So it's a set of numbers, 4 over 3, and that is all raised to the nth power. Again, we're finding the first 5 terms. So basically you're looking at S of 1, S of 2, S of 3, S of 4, and S of 5. So S of 1, this is just 4/3. Plug in 1 wherever you see an n to the first power, which is just 4/3. S of 2, we have 4/3. You see an n as the power, plug in the 2. So we get 4/3 squared, which is 16 over 9. S of 3, so this is 4/3 quantity cubed. Well, 4 quantity cubed is 64. All over 3 quantity cubed is 27. S of 4, we have 4 raised to the all over 3, and that's all raised to the 4th power. So 4 to the 4th is 256. All over 3 to the 4th, which is 81. S to the 5th is 4/3 cubed. I'm sorry, 4/3, not cubed, raised to the 5th power. Which is, just want to make sure I did all my math right. 4 to the 5th is 1024, all over 3 to the 5th, which is 243. Okay, so we found the first 5 terms of that sequence. So we're going to look at special sequences in the next 2 sections. Arithmetic sequences, so they're sequences that have these particular patterns, and geometric sequences. Here, we're going to look at recursive sequences. So what a recursive sequence is where you have terms dependent on other terms in your sequence. So a recursive sequence is when when terms in your sequence are dependent on other terms in your sequence. Okay. So if it's a recursive sequence, basically when they give you the formula, they also have to give you some information about the terms. So if we wanted to find, same example where we're finding the first 5 terms, but if we want to find the first 5 terms of a recursive sequence, and in this example, we're given that a sub 1 is equal to 3. And it's given our nth term, a sub n, is equal to 4 minus a sub n minus 1. Okay, so think about this. We already know what a sub 1 is, so when we're doing sequences, we progress in our integers. So the next integer after 1 is 2. So we would look at a sub 2. So looking at a sub 2, this is equal to 4 minus, now all you're doing is you're plugging in 2 wherever you saw an n. So a sub 2 is equal to this 4 minus the a sub, and then the 2 minus the 1 subscript. So this a sub 2, this is the same thing as 4 minus a sub 1. But like I said, this recursive sequence is where your sequence is dependent on other terms. So your a sub 1 value we're given is 3. So let's go back. We can find what a sub 2 is now. We know a sub 2 is equal to 4 minus a sub 1, which is 3. So a sub 2 is equal to 4 minus 3, which is 1. So to find our third term, we're looking at a sub 3. So go back to your a sub n term. So this says 4 minus a. We're going to plug in 3 wherever we see an n. So 3 minus 1. So a sub 3 is the same thing as 4 minus a sub 2. But we just found what a sub 2 was. And a sub 2 is 1. So a sub 3 is equal to 4 minus 1. So this is equal to 3. So a sub 4 is equal to 4 minus a sub 4 minus 1, but a sub 4 minus 1 is a sub 3. We just found a sub 3, and that was 3. So a sub 4 is equal to 4 minus 3, which is equal to 1. One more. Wonder if you guys can figure out what you would get. Do you see some pattern happening here? A sub 5 is equal to 4 minus a sub 4 minus 1. I'm sorry, a sub 5 minus 1, which is a sub 4. So this is 4 minus a sub 4 is 1. So 4 minus 1 is 3. A sub 5 is 3. So if we look at our sequence, first term was 3, then we had 1, then we had 3, then we had 1, then we had 3. And so we could figure out what it was. What if they gave you a sub 1 was capital A and a sub n? This is equal to n times a sub n minus 1. Oops. That's actually r times a sub n minus 1. And they tell us that r cannot equal 0. Again, we're finding the first 5 terms of this sequence. This is a recursive sequence because, and I can see this without me even telling me, because a sub n is and represented in terms of another term, a sub n minus 1. The term actually that would fall right before that, and we're going to see that today. This actually looks like a geometric sequence, which is the third section in this textbook in chapter 13. Okay, so again, we want to look at a sub 1, first 5 terms. And so we're going to go back in here, wherever we see an n, we're going to plug in 1. And so we have, this is equal to r all times a sub, actually, we already have a sub 1. If you notice that, that would give us a sub 0. We need to look at a sub 2. So plugging in that, we have 2 minus 1. So this is equal to r all times a sub 1. But a sub 1 is given to us. It's just capital A. So this is equal to r times capital A. So a sub 3, this is equal to r all times a sub 3 minus 1, which is a sub 2. If we go back in here and we plug when a sub 2 is, which is r times capital A, and we have that r out front. So this is equal to r times r, which is r squared, capital A, is a sub 4. Wait, no, that was a sub 3. Sorry about that. If we look at a sub 4, this is equal to r times the term right before it, a sub 3. So this is equal to r times the term right before it is above here, r squared, capital A. Well, r times r squared is r cubed, A. A sub 5, this is equal to r times the term right before, a sub 4. Well, this is r times r cubed times A. This is r to the 4th, A. So we have the first 5 terms of the sequence. A, r squared A, r cubed A, r to the 4th A, and then you could probably tell what the next ones are going to be. Okay, so going the opposite direction. So we're looking at a sequence and we're going to try to figure out what the nth term is, what the formula for that nth term is. So the direction states, the given pattern continues in these problems. Write down the nth term of the sequence, set notation a sub n, suggested by the pattern. And so we're given here 1, 1/2, 1/4, 1/8, dot, dot, dot. And we want to find the formula for the nth term. A sub n. Okay, so I noticed we have fractions. If we look at this, you're trying to find patterns. If we look at this, and maybe it would help you if you rewrote that first term so it was a fraction, that's the same thing as 1/1. We have 1/2, we have 1/4, we have 1/8. So I notice that I always have 1 in my numerator. So you just need to kind of play around with this, come up with something that you think would work, and then you always have to go back and check to make sure that what you found was right. So I know that I always have 1 in my numerator. And if I look at my denominator, that 2, 4, 8, I'm noticing that this looks like a 2 raised to an n power. Right? If I have 2 to the first power, I have 2. If I have 2 squared, I have 4. If I have 2 cubed, I have 8. The thing is that I want a 1 down here when I start my first term. And if I plug in the n equals 1 here, that's going to give me a 2. And that just gives me 1/2, which is actually my second term. So in order to compensate, if I subtract 1 here in my exponent, and I plug in 1 now, 1 minus 1 is 0, and it's 0, anything other than 0 raised to the 0 power is 1. And that would give me my first 1 in the denominator, which I needed. And so it would work out now. Any term that we plugged in, any number we plugged in, would give us the correct term in the right spot. So a sub n is equal to the set where we have 1 all over 2 raised to the n minus 1 power. Just seeing if I can find any that, oh, here's one. So we have the set or sequence, and the sequence starts with 2, then it's -4, then it's 6, then it's -8, and then it's 10, comma, dot, dot, dot. So it continues on in that pattern. So if you see something that's alternating in signs, there's a trick. So alternating signs. So positive, negative, positive, negative, positive, negative, or negative, positive, negative, positive. The trick is you're going to take -1 and we're going to raise it to either the nth power, or you can write it as n minus 1 or n plus 1, doesn't matter. depending on, do you want to start with a negative number or do you want to start with a positive number? If I start with n equals 1, which would give me my first term, -1 to the first power is negative. So I would start with my terms alternating in signs with starting with a negative. Where if I wrote it in the form of -1 all raised to that n plus 1 power, when we plug in 1 there, our exponent's going to be even. Raising a negative to an even power is positive. And so that would give us the positive coefficient or value in front. So once you see that it's alternating in signs, you're going to need to determine or know that there's this -1 raised to some power in there with n in it. And then look at it without the sign, so 2, 4, 6, 8, 10. So to me, looking at that, that's an even number. And so we talked about getting even numbers were in the form of 2 times n. And so we can play with this. A sub n would equal -1 raised to the n. I want it positive first, so I need my exponent to be a positive. Oh, I'm sorry, not positive, an even exponent. So n plus 1 would make that even. And then to get an even number, so we can write this as 2 times n. So again, always kind of test it to make sure that it gets you what you want. So if we plug in 1 for our first term, we get -1 squared times 2 times 1. So this is 2. If we plug in 2, wherever we plugged in and put it in our equation, so we get -1, 2 plus 1 power, and this is 2 times 2. Plugging in 2 for n. So this gives me -1 cubed is -1 times 4, which is -4. If I plug in 3, I have -1 to the 3 plus 1 power times 2 times n, which is 3 in this case. So we get -1 raised to the 4th times 6. So this is 6. So you can see that we figured out the correct formula for the nth term. So they might not ask you to list all the terms in the sequence. They might say, okay, now find the 20th term of the sequence. And so all we have to do now is plug in 20 wherever we see n in our sequence. And so if we did that, we have -1 all raised to the 20 plus 1 power times 2 times n, which is 20. And so this is equal to -1 to the 21st power times 40. This is an odd power raising -1 to, so that's going to be -40. Okay, so I'm looking at this one. I'm thinking, this one looks a little difficult. How would we do this? So let's do it. So 1, 1/2, 3, 1/4, 5, 1/6, 7, 1/8. So we're trying to see if there's some sort of pattern happening. The first thing I was actually thinking of was breaking this down actually as depending on, is it even or odd, and having like a piecewise function, but I now don't think that we need to do that. If we ignored the fractions and just looked at it, notice this is 1, 2, 3, 4, 5, 6, 7, 8. So I know that we want to get some number. We want it in that form, right? I also know that if I have this in the denominator, let's look at it this way. Maybe this will help us. So this is 1 to the first power, comma, let's rewrite this in the numerator. So this is 2 to the negative 1 power, comma, 3, let's just write this with an exponent, is a 1 power, comma, this is 4 to the negative 1 power, this is 5 to the first power, this is 6 to the negative 1 power, this is 7 to the first power, this is 8 to the negative 1 power. So if we now think of it this way, notice it as our base, 1, 2, 3, 4, 5, 6, 7, 8. Well, we can just let that be n. So now we need to manipulate it so our exponents are bouncing back and forth between positive 1 and negative 1. And so if we let this be negative 1 raised to the, well, the first time we need it to be a positive 1. And so maybe if we raise that to the n plus 1 power. And we can define our nth term to be that. And so again, it's really helpful to just make sure what you chose was correct. And sometimes it's not, but then sometimes you can see how you can manipulate it to work. And so if we let n equals 1, because that would be our first term of our sequence, this gives me 1 all raised to the negative 1. And this is 1 plus 1, which would be squared. So this is 1 to the first power, which is 1. That's what we wanted in this sequence, so we're good. A sub 2, plugging it in here, we have 2. Raise this to the negative 1 power to the 2 plus 1 power, which is cubed. So this is 2. Negative 1 cubed is negative 1. Rewrite a negative exponent as a positive, bring it down to the denominator. We get 1/2. So notice that this is going to get us what we want, and so we figured out what a sub n really was. Okay, so now these were called sequences. Series are summations, or the sum of terms in a sequence. So notation, I think this is called sigma. So you have sigma here, and we have k here on the bottom equals, and I'm going to put like a little blank here, and I'm going to put a blank on top of this sigma. And then here we're going to have a sub k. So usually, not always, but usually you start with 1. This tells me the term, the value that we're going to plug in. This is our start value for k. And this right here, let's put n here. So this is the nth term, or nth value, or nth term of the sequence. So for instance, okay, and so basically, actually, let's go further. So this right here, this would equal you're going to figure out what the first term is. You're going to plug in 1 into this formula, and you're going to look at a sub 1. Then you're going to add. Then you're going to plug in 2 wherever you see k, just like we were doing, but this time it's k, not 1, or n. You're going to plug in 2 wherever you see a k, and this would give you the formula. That would give you the second term of the sequence, a sub 2. Plus, and you're going to keep adding until you get up to, so a sub 3, dot, 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 a sub n minus 1. Oops. Plus a sub n. So summing the first n terms of the sequence. Not necessarily, though, has to start at 1. So it might have said, let's look at k equals 3 to 5. That would tell me I'm looking at a sub 3 plus a sub 4 plus a sub 5. Again, this bottom one is telling me where I'm starting, and the top of my sigma notation is telling me where I'm ending. Let's look at an example. So we're looking at the summation. K equals 1. Oops. And so I was just looking at how they're doing this. Okay, so k equals 1 of k squared all over 2 of n. Okay, so let's look at this. This a sub k value, this gives us the kth term of our sequence of k squared over 2. And so if we want to look at a sub 1, we're going to go in here, we're going to plug in 1 wherever we see a k. So we have 1 squared all over 2, which is 1/2. So this is going to equal 1/2 plus, now I need to look at what is the second term. So if I look at a sub 2, I'm plugging in 2 wherever I see a k in this. And so I have 2 squared all over 2. So this is going to give me 2 squared is 4 over 2, which is equal to 2. So a sub 3, this is equal to, I see a k here, so I'm going to plug in 3. 3 squared all over 2. So this is equal to 3 squared is 9 all over 2. So plus 9/2. A sub 4, can go on forever. So 4 squared all over 2. This is 16 all over 2, which is, we can reduce to 8. Sometimes doing this, though, it might be helpful not to actually reduce, so you can see actually more of the pattern going on. Plus dot, dot, dot. I'm going to keep on going until I get to this term. So if they had a number here, that's where I stop, but it's telling me n. So how I would write that nth term, I'm going to, instead of plugging in a number where I see k, I'm plugging in n where I see k. So dot, 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 representing I'm going on. And then I would have n squared all over 2. Okay, so this could get really, really tedious. If it told us that we needed to sum 100 terms, than having to figure out what those 100 terms are and then summing them together. And then if they're dealing with fractions, I mean, it just really could get very tedious. So thank goodness there's some formulas that can help us make it simpler and so that it doesn't get long and nasty. So let me give you some of those formulas. But before I do that, actually, let me give you another thing that you need to know, which is factorials. So in factorial, so notation is the n and then an exclamation point. And so this is equivalent to taking whatever that number is that you're taking the factorial of and multiplying it by that times 1 less than that number, so n minus 1, times 1 less than that number, so n minus 2, times 1 less than that number, so that would give us n minus 3, all the way down until you get to 1. So n has to be an integer. Positive integer. And 0 factorial is equal to 1. So if it said 5 factorial, all this is saying for you to do is multiply it by 5 times 4 times 3 times 2 times 1. I break this down. 5 times 4 is 20 times 3 times 2 times 1. 20 times 3, this is 60 times 2 times 1. 60 times 2 is 120 times 1 is 120. Okay, so I noticed on the exam when you had 3 things multiplied together, I don't remember what example, someone was distributing that number to the other items, but if it's strictly multiplication, you don't distribute it. You use order operations and you multiply in that order it's appearing from left to right. So notice that this is going to grow really, really fast. So if we had 10 factorial, this is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So there is a button on the calculator that does factorial. Actually, on this one, I'd have to go into some place to find it. Probability, PRB. So here I would have to type in my number, tell it I want to do a factorial. Oops. And I did 10 factorial. That gives me 3, 6, 2, 8, 8, 0, 0. So that is 3,628,800. Okay, so that's something else that could get really tedious if you had a huge number, 100, and then I have to multiply, 100 times 99 times 98 times 97. Sounds like a song that we used to sing way back when. 99 bottles of beer on the wall, 99 bottles of beer, take one down, pass it around. Anyways, Let's go to another problem. Or actually, let me go to the properties of summations. And let me change my page because my pen's starting not to work. Okay, so some theorems for summations. Summation notation properties. So if A sub n and set and B sub n, so that set, are two sequences, and C is a real number, then the following hold. So we have summation here, k equals 1 to n of C A sub k. Well, basically, if you did this, you would look at C times A sub 1 plus C times A sub 2 plus C times A sub 3 dot 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 C times A sub n. This is so much easier if we just factor that constant outside of the summation. So this is actually the same thing as if we pull the C out front of the summation, and then the summation of k equals 1 of n of A sub n, or A sub k. So I'm going to kind of put 2 and 3 together. But basically this says is if you're looking at k equals 1 to n of some sequence A sub k plus or minus some sequence B sub k, well, this would be saying A sub k, or A sub 1 plus B sub 1 plus A sub 2 plus B sub 2 plus A sub 3 plus B sub 3. So we can just regroup that ordering. And so this is the same thing as saying we can look at the summation from k equals 1 to n of A sub k plus the summation k equals 1 to n of B sub k. Same sort of idea with the minus sign. This would have been A sub 1 minus B sub 1 plus A sub 2 minus B sub 2 plus A sub 3 minus B sub 3. If we group the B terms together and factored out a negative 1, then it could be written as plus or minus, that minus in between, depending, in front of that summation.
What does k equal under the B sub k?
1.
Oh.
Yeah, so it's just that we're, instead of taking, so basically if you have more than one term as your formula, you can break it up as a summation of the first term plus or minus the summation of the second term plus or minus summation of the third term, etc. And there's going to be some form or some ways to simplify depending on how that term looks or what form it's in. So sometimes I said like you don't start with the first value, the positive integer 1. And so let's say that you had started with k equals j plus 1. And we're going to n of a sub k. So this might be saying instead of starting at the first term and going to n, we're starting at the fifth term and summing it up, fifth term up to the nth term. And so if this happens, well, if we look at k equals 1 to n, we take and sum all those terms, and then we subtract off the terms before we get to j plus 1, because we don't want those. So if we subtract off the ones between there, we can say, we can start from equal to k equals j. Let me see what they're. Oh, yeah. K equals 1 to j of a sub k. So if we look at this, again, let me just kind of rephrase this. So if we're looking at, let's say, the fifth term, so k equals 5, to, let's say, the 10th term of a sub k. So what this is saying is we can look at k equals 1 to the 10th term of a sub k minus k equals 1 to the one right below this, which would be 4 of a sub k. And so this right here would say I'm looking at my first term all the way up, I shouldn't go to 10, to the 10th term. I'm almost there. Minus, and this would say I would be subtracting off all the terms from the first term up to the fourth term. So minus a sub 1, minus a sub 2, minus a sub 3, minus a sub 4. When I look at this, notice what cancels out what I want. This negative a sub 1 with this a sub 1, this a sub 2 with this a sub 2, this a sub 3 with this a sub 3, a sub 4, a sub 4. And so this now gives me an example where I'm looking at just the fifth term up to the 10th term. Okay, so let me give you some formulas. So you'll be using summations in calculus when you get into looking at integration. And then you'll be using it a lot more in math. So formulas for sums of the first n terms of a sequence. If you have summation of, let's say, k equals 1 to n of c, where we say that c is just a constant, well, basically all this is saying is you're taking c. There's no k value in here, so each time you plug in or try to plug in that value for k, you're always just getting back that c value. Kind of like a horizontal line. A lot of students have a hard time graphing that horizontal line because every value you plug in for x, there's none. It's always that same y value. And so here, basically, this would be saying that I'm adding c n times. So this is the same thing as saying, if you have a summation of just a constant, you're just going to multiply the number of terms that you're summing times that constant. So if you're just summing I'm not going to put X there, sorry. Let's put K. The summation of K equals 1 to N. So this would be saying, if you plug in 1 here, the first term is 1, plus the second term would be 2, plus 3, plus dot, 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 plus N. You can figure out what that sum of those first N terms are by looking at N all times the quantity N plus 1 all over 2. Okay, I'm going to give you these formulas. You need to know how to use them, but I'll give you these formulas I'm giving you right now on the test. Don't normally give formulas in most classes, but this is one that I do give. It's amazing though, times I give formulas, if students, if you don't understand it, it's not going to help them. Okay. So let's look at 3. You have the summation of K equals 1 to N of K squared. So if we plug in our first value for our first term, we get 1 squared. Plus, if we now plug in 2 for our second term, 2 squared is 4. 3 squared is 9, so plus 16, plus dot, 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 up to the nth term, so n squared. The formula is going to be n all times n plus 1, all times 2n plus 1, that quantity, all over 6. One more. So if we're summing something in the form where you have a cubic, so k equals 1 to n of k cubed, well, 1 cubed is 1, plus 2 cubed is 8, plus 3 cubed is 27, plus dot, 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 plus n cubed. So instead of having to sum up those n terms, you can plug it into the formula that this is the same thing as n times the quantity n plus 1 all over 2. And that whole thing that I just gave you is quantity squared. So let's say we're now going to use this to find the summation from k equals 1 to 26 of 3k minus 7. Okay, so we can sit here and we can find the first 26 terms here and sum them, or we can break this down. So notice that I have a difference here. So I can break this down as 2 separate summations using that difference. So this is the same thing as saying the summation from k equals 1 to 26 of 3k minus the summation from k equals 1 to 26 of 7. I also can pull my coefficient in front. So this is the same thing as the summation, or actually 3 times that summation of just k now. So I'm manipulating it to look like one of the pieces so I can use that formula. So k equals 1 to 26 of just k minus the summation of k equals 1 to 26 of 7. So I can use this formula number 2 that I had said it was number 2. It's not necessarily number 2 in all things. I just, in my notes, it is. So the summation of k, this is equal to the value you're going up to. And so in our case, this n value is 26. Let's bring down that 3 so we don't forget about it. So my n value again is 26. So 26 all times my n value plus 1. So 26 plus 1 is 27, all over 2. Minus, well, if I look at the summation of a constant, it's just that constant times how many we're summing, which is 26. So minus 7 times 26 or 26 times 7, it doesn't matter. Okay, so I was thinking that we can simplify. I was thinking actually we could factor out a 26 and that might actually help us simplify it faster. But I'm just going to plug it in. So 3 times 13 times 27 minus 26 times 7. So first grouping, I get 1053 minus 26 times 7. That's 182. Which is equal to 871. So find the sum of each sequence again. Let's see. What if it said the summation of k equals 8 to 40 of negative 3k? Well, we can factor out there, bring the negative 3 outside of our summation. So this is the same thing as negative 3. Summation from k equals 8 to 40 of k. So we want to first look at, we only know how to do these formulas from 1 to the number. So we need to rewrite this. And this is where that 1 formula was helpful. And so we're going to go out from 1 to 40. So k equals 1 to 40. Okay. And then we're going to subtract off the terms we didn't want. We don't want the first 7 terms in here. So we're going to look at the summation from k equals 1 to 7 of this k. Okay, so using our formula, let me see if I can pull it down here. So actually, let's pull it down. I'm just going to put it down here. So if this had been which we have. So our case here, our n is 40 for the first summation. And so we have 40 times 40 plus 1, so 41, all over 2, minus, and so now we're going to look at n being 7. So we have, plugging in this formula, 7 times 7 plus 1, which is 8, all over 2. So we could really technically factor out the 2 if we wanted to, but we really don't have to. So 40 times 41, it's 1,640, minus 7 times 8, which is 56, all over 2. So 1,640 minus 56, that gives you 1,584. That's divided by 2. We still have a negative 3 out front. That divided by 2 gives you 792 times negative 3 gives you back negative 2,376. Which again is a lot faster than having to find the 8th term, the 9th term, the 10th term, all the way to the 40th term, and then go back and have to sum all of those terms up, those 32 terms up. Okay, so the next 2 sections are special sequences, and those are called arithmetic and geometric. Arithmetic basically is where you're taking a term before and you're summing something to it, the same constant to it. Geometric is basically you take a term and you're always multiplying it by the same constant to get the next term. So let's, before I jump into that, let's take a break. But knowing now the general thing between the sequences and series, hopefully the next 2 sections will come out pretty easily. I am going to do a couple of proofs because you're going to need to know the formulas for arithmetic and geometric sequences. I'm going to derive a couple of the proofs or different forms for that formulas so that it's kind of easy to remember. If you don't have it memorized, you can derive it really easily, knowing what the definition is. So again, let me pause the video, we'll take a break and then come back and look at those. Okay, so we just discussed what a sequence was and what a series was. And now we're looking at arithmetic sequences. Arithmetic sequences are a special type of sequence. So an arithmetic sequence is a sequence whose term is found, or whose term can be found by adding a constant d. D is called the common difference. Okay, basically what this is saying is I can get any term if I know the term before it. So I can represent the term before a sub n as a sub n minus 1. Knowing that term and adding that constant, some constant is always going to be the same constant d. So this is one formula that you need to know what it means to be an arithmetic sequence. And this is one of the formulas that's going to be helpful. So the other two formulas that are helpful, we can derive by this right here, knowing that what the definition of an arithmetic sequence. A term plus the term, or a term plus some constant equals the term, right? Next term. Notice I can solve for d here. D is equal to, I can just subtract a sub n minus 1 on both sides. D is equal to a term minus the term right before it. In order to be arithmetic, this has to be the same number each time. If you took the 10th term minus the 9th term and you got some constant, but then you took the 5th term minus the 4th term and you got a different constant, then this was not an arithmetic sequence. Always has to be the same. To derive the next one, so to derive the next formula, deriving the third formula. For an arithmetic sequence. Basically, what this formula is saying is if I want to get the second term of my sequence, we have some a sub 1. If I want to get the second term, this would equal my first term plus d. If I want to get my third term in my sequence, by the definition, I would have to look at my second term and add d to it. We're going to try to rewrite this form of an arithmetic sequence in terms of the first term a sub 1 and d. So let's go back in and I am going to use substitution. We know what a sub 2 is from up here. And so I'm going to go back in and I'm going to substitute what a sub 2 is in terms of a sub 1 and d. And a sub 2 is a sub 1 plus d. And then I have this plus d over here. So let's combine like terms here. And so a sub 3, this is equal to a sub 1. D plus d, though, is plus 2d. So I'm going to box these because we're going to come back to them. And it's going to be helpful to see a pattern going on. So we have a sub 1, we have a sub 2 is a sub 1 plus d, a sub 3 is a sub 1 plus 2d, a sub 4, well, this would be, by definition, the term right before it, a sub 3 plus d. But we know what a sub 3 is from up here. A sub 3 is the same thing as a sub 1 plus 2d. And then let's bring down the other d plus d. Always go the wrong way. Plus d. And combine like terms. So we have a sub 4 is equal to a sub 1 plus 2d plus d gives us 3d. So I can keep going, but hopefully you notice this pattern. So notice they all have a sub 1 here, plus some coefficient d. Well, notice a sub 2 is 1d, a sub 3 is 2d, a sub 4 is 3d, If you did a sub 5, this would be a sub 1 plus 40. So a sub n is equal to the first term plus n minus 1 times d. So this is the third formula that is going to be really useful when we're solving some of these problems. Let me pull an example. Okay, so it says the following: show that each sequence is arithmetic. Find the common difference and list the first four terms. So show that each sequence is arithmetic. Find the common difference. And find the first four terms. Okay, so let's say we started with a sub n. That is a sequence, and that sequence is equal to 3n plus 1. So we want to show that this is an arithmetic sequence. So we need to show that if we took a term minus the term right before it, we always get back the same constant, d. So we need to show that if we took some term a sub n minus some term right before it, a sub n minus 1, that this has to equal d, where the d is a constant. Okay, well, we're given what a sub n is, right? A sub n is just 3n plus 1. Minus, okay, I need brackets here. Now I need to figure out what a sub n minus 1 is. So I need to go back into my equation up here, and wherever I see an n, I'm going to replace it with n minus 1. So I have a 3. I see an n there. I'm going to put parentheses. I'm going to replace that with n minus 1, and then I have a plus 1. Close my bracket. So let's simplify. So simplifying the following, I have 3n plus 1 from below, from here. I'm going to write it below. Minus, let's distribute our 3 here. Order of operations, first work inside the most inner parentheses, and minus 1 can't be simplified. We're going to distribute, so we get 3n minus 3, and then bring down that plus 1. Combine terms, like terms inside that bracket. So we have 3n plus 1 minus, combining like terms, we have 3n negative 3 plus 1, so we have minus 2 inside that bracket. Let's distribute this negative, bringing down our 3n plus 1. We have negative times 3n is negative 3n, and negative times negative 2 gives us plus 2. combining like terms now. We have 3n minus 3n cancels, and we have 1 plus 2 gives us 3. We got that d is equal to 3, so this is our common difference. We showed that this is a constant. If you had gone through this process where you had looked at the a sub n term minus the a sub n plus 1 term, and you went through and simplified and you didn't get a constant, you still had n, the variable, left in there, then it's not an arithmetic sequence. But since we did that and we were just left with a constant, then it's arithmetic, and that is the common difference. Then it told us that we wanted to find the first 4 terms. So we showed it was arithmetic, we found the common difference in the first 4 terms. So a sub 1, you're just going in here and you're plugging in 1 wherever you see an n. So you have 3 times 1 plus 1, which is 4. A sub 2, go back in wherever you see an n, plug in 2. So you have 3 times 2 plus 1. So this is 6 plus 1, which is 7. A sub 3, 3 times 3 is 9, plus 1 is 10. A sub 4, our 4th term is 3 times 4, which is 12, plus this 1 is 13. So let's show S sub n, which is equal to the natural log of 3 raised to the nth power. Okay, so actually this is same directions. So let's just say this was part B. Part B, another example. This time we're going to show that the natural log of 3 raised to the nth power is arithmetic. We're going to find the common difference, and we're going to find the first 4 terms. So showing it's arithmetic, we want to find out what d is. D is equal to the term S sub n minus the term right before, S sub n minus 1. So if I'm looking at the natural log of 3 raised to the nth power minus, so let's go back in here wherever we see an n, except for the natural log n part, we're plugging in n minus 1. So we have the natural log of 3 raised to the nth minus the natural log of 3 raised to the n minus 1 power. We have to show that that's a constant. So let's use some rules. So I notice I have a minus in there, a minus in between my natural logs. I can rewrite that. So this is the same thing as the natural log, parentheses, 3 raised to the nth power all over 3 raised to the n minus 1 power. So now that we rewrote this, we can now use rules of exponents. So this is the natural log of 3, same base. So I'm taking my exponent on top, which is n, minus my exponent on my bottom, which is n minus 1. So if I distribute that negative, so I get the natural log of 3 all raised to the so n minus n power, and then a negative times a negative 1, so this is plus 1. So this is the natural log of 3. Well, n minus n cancels in that exponent, and so we're just left with a 1 in the exponent, which we don't have to write. And so notice how we get natural log of 3 is what D is. And that is a constant. We are no longer left with N in our expression. So finding the first 4 terms, S of 1. So that would be the natural log of 3 raised to the first. S of 2, this would be the natural log of 3 squared, or natural log of 9. Or another way I could have written this was 2 natural log of 3, right, using rules of exponents. S of 3, so if I go back in here and I plug in 3 wherever I see an N, where's my equation? We have natural log of 3 cubed, which is the natural log of 27. Or another way we could have expressed that was 3 natural log of 3. All equivalent. And so 4 is a natural log of 3 raised to the 4th. Natural log of 81, or the same thing as 4 natural log of 3. Okay, so now we know what an arithmetic sequence is. Now, if we are given information about that sequence, we should be able to find formulas for the nth term. We should be able to find the common difference or the first term, depending on what they're asking. So given the information for the following, so find the nth term of an arithmetic sequence, a sub n, whose first term a sub 1 and common difference d are given. What is the 51st term? Okay, so if you were given, so we want to find a sub n, and I'm going to change it to the 25th term. So you're given that a sub 1 is equal to -2, and d, your common difference, is equal to 4. So this is where that third formula that we derived would be very helpful. So we know the nth term can be written given the first term, a sub 1, plus n minus 1 times d. So basically, we can now figure out what the nth term is. We know what a sub 1 is. We're given a sub 1, so we can plug it in here. And we're given what d is. And d is 4. So we know that a sub n is equal to the first term plus n minus 1 times d. And we're given what d is. So a sub n equals -2 plus n minus 1 times d, and d in this case is 4. Make sure you have parentheses around the n minus 1. So you can leave it like this, or you can simplify. Notice if we distribute this 4, we're going to have some like terms. So a sub n technically is equal to -2. Distribute our 4, we get plus 4n minus 4. So a sub n is equal to -2 minus 4 is -6 plus 4n. This form right here will be easier when you find the terms that you need to find. This way right here, the first way I boxed, you can see what the first term is pretty easily and what d is in this form. So now it wanted the 25th term. So it wants a sub 25. So all you're going to do is you're going to go back into a sub n, and wherever you see a 20 or n, you're going to replace it with 25. So you have negative 6 plus 4 times n, so 4 times 25. So you have negative 6 plus 4 times 25 is 100. So negative 6 plus 100 is 94. So the 25th term of our sequence is 94. So let's say instead you were given not the first term or what your common difference is, but this time you're given what the 90th term is. Or you want to, you don't want to find that. You're given terms of the sequence. Are the following: 3, negative 3, negative 9, dot, dot, dot. You're also told that it's an arithmetic sequence. And you want to find a sub n and the 25th term. Well, they gave us enough information that we can find a sub n. A sub n, again, one way to find this is it's our first term, a sub 1, plus n minus 1 times d. Well, you're given the sequence, right? And so our first term, well, the first term listed, that's a sub 1. So a sub 1 is equal to 3. And then we need to figure out what d is. We're given this as arithmetic, so if we took a term minus the term right before, that's what d is. So we're given it's arithmetic. So we know d is equal to a term minus the term right before it. Well, we're given terms in the sequence. So d could be the same thing as a sub 2 minus a sub 1. So d could equal the second term, which is negative 3, minus the first term, which is 3. So I get d is negative 6. Notice if you had taken the third term, which we are given, minus the second term, you better get back negative 6 or something's wrong. So let's just show it. Negative 9 is our third term minus our second term, which is negative 3. So this is negative 9 really plus, minus a negative is plus 3, which is negative 6. Okay, so we got d is negative 6 and we got a sub 1 is 3. And so now we know what our a sub n term is. So a sub n is equal to our first term, a sub 1, plus n minus 1, all times d. Well, a sub 1 we found to be 3, and d we found to be negative 6. Okay, so we can leave it like that, or we can simplify it by distributing the negative 6 and combining like terms. So a sub n, if I distributed my negative 6, I'd bring down my 3. Negative 6 times n is negative 6n, and negative 6 times this negative 1 is plus 6. So a sub n is equal to 3 plus 6, which is 9 minus 6n. That's another way you could have rewritten it. It wanted us to find the 25th term. To me, it's easier to plug it into the second form, but you could plug it in here and you would get the same thing. 9 minus 6 times n, which is 25. So 9 times 6 times 25. 6 times 25, that's 150. 9 minus 150 is negative 141. Does that kind of make sense? Look at your result. Would that make sense? If I kept on subtracting 6 here from the term right before it, would it make sense that I would get down to negative 141 on the 25th time? Which makes sense to me. Okay. Actually, same rules. This time you're given that you have a sequence. So you're given your sequence. Is 2 square root of 5, 4 square root of 5, 6 square root of 5, ... Find a sub n. And you're given its arithmetic. Okay, so same idea. We can use that formula if we have the first term plus n minus 1 times that common difference d. So we can figure out what d is by looking at this sequence, and we can also figure out what our first term is, because it's given the list and it's given what the first term is. It just doesn't denote it like that. But first term here is 2 root 5, and then I can figure out what d is. D is equal to any term minus the term right before. So a sub 2 minus a sub 1 would be the same thing. It should be the same thing as a sub 3 minus a sub 2. So it doesn't matter which one you choose. So if I did 6 root 5 minus 4 root 5, rules of adding and subtracting radicals, same radical, same index, so we can just add or subtract the numbers in front. 6 minus 4 is 2, and then root 5. That's our D. This is our A. And so a sub n, that's our a sub 1. A sub n is equal to our first term, so 2 root 5, plus n minus 1 times d. And d is 2 root 5. Same thing. Notice if we simplify by distributing that 2 root 5, we have 2 root 5 plus 2 root 5 times n. I put that in parentheses. Minus 2 root 5. We have a 2 root 5 minus a 2 root 5. That cancels. So we have a sub n is equal to 2 root 5 times n. So a sub 25 is 2 root 5 times 25. So this is 50 root 5. But knowing this, a sub n, we know the nth term, and we can find any term that it asked us to find. Okay, so summations, so theorem for summation of arithmetic sequences. So if we're going to sum the first n terms of an arithmetic sequence. Okay, so we're going to suppose that a sub n is arithmetic. And a sub 1 is the first term. And d is the common difference. Then the summation of a sub k, k equals 1 to n, is equal to a sub 1 plus a sub 2 plus a sub 3, same situation, dot, 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 plus a sub n. So summing all those n terms. It ends up that this is the same thing as n divided by 2. 2a sub 1 plus n minus 1 to the d. But if you simplify this, basically it's n over 2 all times a sub 1 plus a sub n. So basically you need to just know how to apply it. So we'll give that to you on the test. So let's look at an example. If we have a summation of n equals 1 to 90 of 3 minus 2n. So find each sum. So I can break this down as we did before, or I can use this formula. I might ask you first to show me that this is arithmetic, and so you should be able to show me that this 3 minus 2n is arithmetic. Seems like that was similar to what we just did. Then we can use this formula. Our n value is what we're summing, so we're summing up to the 90th term. So n in our case is 90. How they phrased it in here, n. Okay, and then the first term, well, if we plug in 1 here for n, we have 3 minus 2 times 1. So we have 3 minus 2 times 1. So that's 3 minus 2, which is 1. We know what the first term is, and we can find the 90th term. So plugging in 90 where we see an n in our equation. So we have 3 minus 2 times 90. So this is 3 minus 180. 3 minus 180 is negative 177. So the summation here is equal to n, which is 90, all divided by 2, times a sub 1, which is 1, plus a sub 90, which is minus 177. So let's simplify it. So 90 divided by 2 is 45, times 1 plus negative 177. So negative 177 plus 1, that's negative 176. So times 45. So this is equal to negative 7,920. So I think what I'm going to do is I'm going to go into geometric sequences and series really quickly. Probably just going through what I had done similarly with arithmetic sequences and series. And then tomorrow we will look at some applications with using sequences and series, as well as starting reviewing for the final. So let me get to a new page and we're going to talk about geometric sequences first. So the last section we need to cover, last material that you need to cover in college algebra. So geometric sequences and series. So just like an arithmetic sequence, it's a sequence that's special. Arithmetic, we summed some common difference, some constant from one term to get to the next term. For a geometric sequence, basically to get from one term to the next term, you're multiplying by some constant. And we call that constant the common ratio. So a geometric sequence is a sequence where the multiple of a term right before and some constant they use R as that constant, R, which is called the common ratio. Gives you the next term in the sequence. Okay, so there's 3 important formulas, and these 3 formulas are going to help you in this section and solving problems. So just looking at what this is saying, basically what this says is if I'm going to get some term a sub n, and it's a geometric sequence, then I can take some multiple, some r, times that term right before it, a sub n minus 1. So here's one formula that's really important. So let's look at what R is. R, if I get R by itself and I divide both sides by a sub n minus 1, R is the same thing as taking a term divided by the term right before it. And so I'm going to derive the third one, similarly to how we had done the third one for the arithmetic sequence. Let me just give you what it is though. And this one is in terms of a sub 1 and R. So a sub n is equal to the first term, a sub 1, times R raised to the n minus 1 power. If you didn't remember that formula though, it comes out pretty easily in how to derive it. So let's look at definition. Okay, so we have our first term, and by definition, a sub 2, this is equal to R times a sub 1. It's equal to some constant times the term right before. A sub 3, this is equal to some constant R, same constant as before, times the term right before, which is a sub 2. So I'm going to do the same thing I did before. I'm going to use substitution. So I know what a sub 2 is though. A sub 2 is the same thing as R times a sub 1. So I can rewrite a sub 3 as this is equal to R times a sub 2, which is R times a sub 1. So a sub 3, this is the same thing as R times R, which is R squared. There's no addition here. This is just one term times a sub 1. Usually you'll see it where a sub 1 is first. I'm going to rewrite it as a sub 1 times R squared. That's my a sub 3 value. Let me just box my a sub 2 value. Or actually, let's write it this way. A sub 2 equals a sub 1 times R. We can continue in this form. So by definition, a sub 4 is equal to R times the term right before a sub 3. R times, but a sub 3 is the same thing as the first term times R squared. This is the same thing as a sub 1. R times R squared is R cubed. So a sub 4. Notice that each one of these, we have a sub 1 in our formula. Then we have our common ratio, R. And then notice for a sub 2, this is to the first power, R is to the first power. A sub 3, R is squared. A sub 4, R is cubed. So a sub n, it's going to be R raised to the n minus 1 power. So that is going to help us in these. Okay, so we want to show that the following is sequence is geometric, and then we want to find the common ratio and list the first 4 terms. So show the sequence is geometric. Find the common ratio. And the first 4 terms. Of the following. So let's say S of n is equal to 7 all raised to the n divided by 4th power. Okay, so we want to look at what it means, again, to be geometric. So it's geometric if we can divide a term divided by a term right before it. Term divided by the term right before it is always going to give us some constant, r. So this is our s sub n term, or in our case, this is s sub n over s sub n minus 1. So s sub n, we're given that. So this is, as r is equal to 7 raised to the n over 4 power divided by, now all we're doing is wherever we see an n here, we're replacing it with n minus 1. So this is 7 raised to the n minus 1 over 4. So rules of exponents. Division, you want to subtract exponents. If we have the same base, we can do that. So we have n divided by 4 minus the exponent on the bottom, n minus 1 over 4. Be careful, we have to distribute that negative outside of that parenthesis for second fraction to the numerator. And so this gives us 7. And then we have n over 4, here we have negative n plus 1. So we have 7, n minus n in the numerator of the exponent cancels. So we have 7 raised to the 1/4 power. So there's no n left in there when we looked at the common ratio of a term and a term right before it. And so that shows that it's geometric. And we want the first 4 terms. And so all we're doing is going in here and plugging in 1 for n, 2 for n, 3 for n, and 4 for n, and just simplifying. So s sub 1 is equal to 7 raised to the 1 over 4 power. S sub 2, this would be 7 raised to the 2 over 4 power. S sub 3 is equal to 7 to the 3 over 4 power. S sub 4 is equal to 7 to the 4 over 4 power. So this is 7 to the 1/2, 7 to the 3/4 doesn't reduce, but 7 to the 4 over 4 does reduce. Sometimes it's not helpful to reduce these because then you don't see the pattern, and if you were going backwards, it would be hard to do that. So if I wrote it out in reduced form, well, the first 4 powers, or first 4 terms, I would have 7 to the 1/4, 7 to the 1/2, 7 to the 3/4, I guess you might be able to see that, 7 to the first power. Where it might be easier to see 7 to the 1/4, 2/4, 3/4, 4/4. The pattern going on. So given information about a geometric sequence, you should be able to find the formula for the nth term. So if you're given a sub 1 is 0, and r is equal to 1 over pi. Find a sub n, and let's say a sub 20. And you're given it's geometric. A sub n is the first term, all times r raised to the n minus 1 power. What's going to happen here? Actually, this is an interesting one. Where did I just grab that? Because if that's 0, we're always going to get 0. And then if you divide by 0 to get the next term, that's undefined. So that's why I'm just a little confused that they have a sub 1 as 0. And I have to look in the back of the book to see. Hold on, let me pause. Okay, so nothing's wrong. We're doing this right. So a sub n is equal to the first term, which is 0, times r, which is 1 over pi, raised to the n minus 1 power. So a sub n is equal to, well, 0 times anything is 0. So a sub n is 0, our nth term. And to find the 20th term, well, there's no n in here, so it's always going to be 0. Any term is always going to be 0. So same idea. You have a geometric sequence. You're given information. You're trying to find a sub n and some term. And so let's say that you're given that you have a sub 3 is 1/3. Actually, let's do it. And a sub 6 is equal to 1 over 81. Okay, so we're given two terms. Fortunately, they're not two terms that are right next to each other. We're given that as a geometric sequence, and we want to find a sub n. So for geometric sequence, it's always helpful to figure out what your first term is and what r is. If we can find a sub 1 and r, then we know then a sub n is equal to the first term times r raised to the n minus 1 power. Well, let's go back in and let's rewrite a sub 3 in terms of this a sub 1 and r. So by definition, if I plugged in 3 in here, right, a sub 3 is equal to the first term times r n minus 1, so squared. Well, I know what the value of a sub 3 is. I know that a sub 3 value is 1/3. So I know 1/3 is equal to the first term, a sub 1 times r squared. So we have one equation that has a sub 1 and r in it. And this other information also gave me enough information that I have an equation within terms of a sub 1 and r. So a sub 6, so now I'm going in here. I know my a sub 6 is equal to my first term, a sub 1, times r to the n minus 1 power. So 6 minus 1 is the 5th power. But again, we're given what our sixth term is. It's 1 over 81 is equal to the first term, a sub 1, r to the 5th. So we have a second equation. So we have two equations, two unknowns. So we're going to use, we have a system of nonlinear equations. which we did in this course. So we want to figure out what this is. We have two equations, two unknowns. So one thing that we can do is we can look at equation 1 divided by equation 2. Notice if we have equation 1 divided by equation 2, the a sub 1 term would go away. Other thing we could do is we could solve for a sub 1 in terms of one of these, or r in terms of one of these equations. If we divide equation 1 by equation 2. So 1/3 is equal to a sub 1 r squared. We're dividing this equation here, 1/81 divided by a sub 1 r to the 5th. Actually, probably would have been better if we did flopped it, but it's okay. We're going to get the same result. So basically we have a complex fraction, 1/3 over 1/81. So 1/3 divided by 1/81 is 1/3 times 81/1 equals, notice our a sub 1's cancel. R sub 2 is divided by R sub 5. Well, the same thing as 1/r cubed. I want to solve for r. So 3 goes into 81 27 times. So I have 27 is equal to 1/r cubed. Clear our fraction. We have 27r cubed equals 1. Divide by 27, we have r cubed equals 1/27. Take the cubed root of both sides. Cubed root of 1 is 1. Cubed root of 27 is 3. If we know what r is, we can figure out what the first term is. So we want to go back and use substitution. To figure out what our first term is, a sub 1. Looks like that first equation might be easier. So we have 1/3 is equal to a sub 1 times r squared. So r is 1/3 squared. Solve for a sub 1. We get 1/3 is equal to a sub 1 times 1/9. We get a sub 1 by itself. We can multiply both sides by 9. We got 9 times 1/3 is 3 is equal to a sub 1. So we have r and we have a sub 1. It's a geometric sequence. So a sub n equals a sub 1 times r to the n minus 1. So let's plug it in. So a sub n is equal to the first term, 3, all times 1/3 raised to the n minus 1 power. So given information about multiple terms in the sequence and telling it that being told that it was geometric, we were able to find what that nth term is and the formula for that. So now if they wanted us to find any term, so if they wanted us to find the 100th term, we can plug in 100 wherever we see an n, and that would give us what the 100th term was. So that actually is a good spot to stop. I didn't get as far as I wanted it in here, but that's fine. All we have really left in this section is looking at summations. So I haven't given you the formula for that yet. And then going back and looking at some applications of arithmetic geometric sequences and series. Let's pause this for today or stop it for today, the recording.